has is not rotting bacteria. That's the wrong answer almost everyone gives. The yellow-green color you see in an infected cut is something else entirely. It's a body count, written in chemistry. Here's what most people picture. Bacteria multiply in a wound. The tissue around it rots, and that rot turns yellow. Bacteria did invade, but they aren't what's coloring the fluid. To find the real culprit, start by ruling out the obvious suspect. Bacteria themselves are nearly colorless under a microscope. They don't carry pigment, so something else is staining the wound. The next suspect, your own immune cells, specifically neutrophils, the first white blood cells that show up to fight an infection. Neutrophils move fast. They can reach a wound site within an hour of bacteria getting in. Once they arrive, they don't politely surround the bacteria. They attack directly using a chemical weapon stored inside their own cells. That weapon is an enzyme called myeloperoxidase, a protein that builds bleach-like compounds to destroy bacteria on contact. Myeloperoxidase works fast, brutally fast. It rips electrons off chlorine atoms and forces them to react with bacterial membranes, tearing the bacteria apart from the outside in. But here's where the trail gets interesting. Myeloperoxidase isn't just a weapon. It's also a pigment. Inside the enzyme sits a heme group, a ring-shaped structure built around an iron atom. That same iron-heme structure exists in your blood, where it makes hemoglobin red. In myeloperoxidase, that structure absorbs light differently. It produces green instead of red. So every neutrophil in a wound is carrying a tiny packet of green pigment built right into its main weapon. Now follow what happens during the fight. Neutrophils don't survive the battles they start. Many die within hours of releasing myeloperoxidase. Some rupture completely, spilling their contents into the wound. That's the moment the color appears. Thousands of dead neutrophils, each one leaking the same green-yellow enzyme, pooled together in the same spot. The fluid you see isn't bacterial waste. It's a graveyard. Picture a single soldier carrying an olive green grenade. One grenade barely changes the color of the ground. Now picture thousands of soldiers detonating the same grenade in the same trench. The trench floor turns the color of the explosive, not the color of whoever they were fighting. That's exactly what's happening under a bandage. The pus isn't proof that bacteria won. It's proof that your neutrophils showed up, fought, and died doing their job. This explains something else people get wrong. Pus color is often used to guess how bad an infection is. Greener pus, worse infection, that's the assumption. But greener pus usually means more neutrophils responded, not necessarily more bacteria. A small cut with an aggressive immune response can produce thicker, greener pus than a larger wound with a slower response. The color tracks your defense, not the size of the attack. There's a stranger layer to this. Doctors in the 1800s sometimes used pus color as a diagnostic clue, decades before anyone identified myeloperoxidase. They were reading immune activity. They just didn't know what they were reading. Even today, this same enzyme shows up somewhere unexpected. Certain rare genetic conditions involve myeloperoxidase deficiency. People with this condition can still fight infections. But their pus often looks different, less green, sometimes barely colored at all. Same battle, different evidence left behind. So the next time you see pus, you're not looking at decay. You're not looking at bacteria's mess. You're looking at chemical residue from a fight your body already won. The pus on your skin isn't a stain left by germs. It's a yellow-green casualty report written in the same pigment that won the fight. If this surprised you, subscribe. We post a new body mystery every day.